The universe is 13.8 billion years old, but spans 46 billion light-years because space constantly expands. With light's speed limit, staring across these distances means looking back in time. We are capturing light born shortly after the Big Bang. To capture that ancient, exhausted light, NASA built the James Webb Space Telescope. Its 21-foot gold-coated mirror was engineered to detect the faint infrared glow of the earliest eras. This data allows astronomers to conduct high-stakes archaeology, unearthing the specific sequence of physical events that birthed the first galaxies. Almost immediately, Webb found something puzzling lurking 600 million years after the Big Bang: thousands of tiny, incredibly bright crimson smudges. Astronomers started calling them little red dots. The community grew concerned when researchers measured the starlight coming from these smudges. To shine that brightly, these objects required a density of stars that defied standard growth models. This scatter plot illustrates the problem. If you map the mass and brightness of early galaxies, there is a strict physical limit to how quickly they can form. These red dots sat in an impossible zone above that line. There was simply not enough time in the history of the universe for objects this massive to coalesce. Either Webb's sensors were misreading the light, or our foundational model of the universe was broken. To solve the mystery, researchers needed a better look. They zeroed in on one heavily magnified dot cataloged as GLIMP-SE 17775. They relied on a natural phenomenon called gravitational lensing. A massive cluster of closer galaxies sat perfectly between us and GLIMP-SE 17775. That immense mass warps the fabric of spacetime, acting as a giant magnifying glass for the light traveling behind it. That magnification allowed Webb to capture an incredibly deep 30-hour exposure of the dot, breaking its faint glow down into a detailed spectrum, a cosmic barcode of its chemical makeup. Because of that stroke of cosmic luck, astronomers finally had the exact raw data they needed to pry open the anomaly and see what was running the engine inside. A standard star, much like our very own sun, burns by crushing hydrogen atoms together deep within its core. That nuclear fusion leaves a very specific, predictable signature in the light it emits. The light pouring out of GLIMP's 17775 completely contradicted that signature. Looking at this spectral graph, researchers identified over 40 distinct spikes, or emission lines. Instead of a neat, organized pattern, the signature was violently erratic. Within this dense cluster of 16 spikes, the iron forest, we see the fingerprints of a high-energy source, powerful enough to strip iron atoms down to their bare essentials. This requires energy levels far beyond standard stellar fusion. Furthermore, the bases of these spikes are wide. This indicates electron scattering, an effect that occurs when light has to fight its way through an incredibly dense cocoon of gas. These specific data points, the iron signatures and the scattering effect, point directly toward a rapidly accreting supermassive black hole. This evidence suggests a hybrid structure known as a black hole star, where the power of a singularity is masked by a massive shell of gas. Here is how a black hole star actually operates. At the center sits a supermassive black hole, gorging on matter at an extreme rate, but trapped inside a dense envelope of gas. Normally, an actively feeding black hole blasts out intense X-ray radiation, which telescopes can easily spot. In this structure, that thick outer cocoon acts as a shield, trapping and absorbing those X-rays. As that gas absorbs the extreme radiation, it heats up and re-emits the energy at lower frequencies, shifting the outward glow into the red spectrum. By swallowing their own X-rays and glowing red, these violent predators of the early universe managed to disguise themselves as harmless little red dots. This mechanical explanation resolves the mathematical contradictions that initially worried researchers. Because that intense brightness is generated by a single, highly efficient black hole engine, rather than trillions of stars, the objects no longer violate our timeline of cosmic growth. Our early universe functioned as an extreme laboratory where gravity and radiation blurred the boundaries between typical bright stars, massive floating gas clouds, and supermassive black holes. It took decades of engineering, a globe-spanning team of researchers, and the most sensitive infrared sensors ever flown to pull this puzzle apart. Our model of the universe was never broken. We just finally built a tool powerful enough to reveal its most extreme rules.